So one of the big ideas in this module is the idea of energy conservation. And I wanted to sort of tie back to some of the sort of system boundary ideas a little bit in talking about energy conservation. For that, we're going to use one of the sort of archetype types of examples. So we're going to imagine we've got some mass that's on a spring. The spring constant has a spring constant K. And we'll say when the mass is at rest, it's sitting at a position x equals 0. Right? And this is very much a sort of standard textbooky problem. But the point I want to make with it is this sort of idea of energy conservation and how thinking about system boundaries relates to energy conservation. So there are a couple of ways that we could actually think about system boundaries for this. One way to think about the system boundary is actually to include both the mass and the spring inside of the system. And if we think about the sort of places that energy can be stored in this system, one place that energy can be stored is in the kinetic energy of the spring, or the kinetic energy of the mass, right? So you've got this mass that could be moving, right? And when it's moving, it's going to have a kinetic energy that's associated with that motion. A second place that energy could actually be stored in this system is in the spring, right? There are interactions in this spring. So at an atomic level, there are atoms that don't want to be pushed too close together or pulled too far apart. And so the spring actually has associated with its state a potential energy that has to do with how much those atoms are being pushed together or pulled apart. So this is the potential energy of the spring. And if we think then about this system, and we ask the question, well, can energy cross these system boundaries? The answer probably, assuming there's not any friction in the system, is no. There aren't any mechanisms or there are no interactions with the outside world which would allow energy to cross back and forth. So we could actually draw a sort of stock and flow for this picture and say we have the kinetic energy of the mass, we have the potential energy that's in the spring, and there's some flow back and forth between the two. So what happens is you might have a lot of kinetic energy at one point in time that then turns into potential energy, turns back into kinetic energy, and so on and so forth. So if we actually imagine the case where we sort of displace this thing, right? Let's say we stretch the spring out. So the spring is stretched out, got the mass over here. And then we let it go. Well, initially, we've stretched this spring. So for this keyframe, number 1, the potential energy is bigger than, let's say, 0. We'll say that the potential energy is defined as 0 at this point. As the mass begins to move to the right, to the left, some of the potential energy that's stored in the interaction in the spring is lost to kinetic energy in the mass, right? So now the mass is moving some. You still have some potential energy here in the spring because the spring is still stretched. When you get back to the sort of center position, right, this is x equals 0. At this point, now the mass is really cruising over to the left, so you've got quite a bit of potential of kinetic energy in the mass, but there's no potential energy in the spring. And then finally, a little later, the spring is compressed some. So again, we have potential energy that's in the spring, and maybe by this point, the mass has come back to rest. So the kinetic energy in the mass is 0. So you can sort of imagine for this framing actually plotting versus time what each of these quantities looks like. So the potential energy you said starts out large, right? It actually drops to 0 at this point when the mass is at the center, and then actually goes back up again as the spring becomes compressed, right? Reaches the maximum when the spring is at maximum compression, drops back to 0 a little bit later when the mass is actually passing back through 0, right? So this is the point of max stretch. This is the point when the spring is relaxed, and this is the point of max compression. Right, so if we say that the potential energy versus time is that it's all aligned, we can also think about what the kinetic energy looks like. The kinetic energy when we start out is 0 because the mass isn't moving. As time goes on, the mass will accelerate. At the point x0, when the mass is moving its fastest, you'll be at maximum kinetic energy. It'll drop back to 0, and so on, so that if you were actually to add these both together, you would actually get a constant because of the fact that there's no mechanism for energy to enter or leave the system. Now, you could also equivalently say, a second way to think about this would be to say, actually, let's draw our system boundary here, right? if we draw our system boundary here, so let's call this system boundary A and this system boundary B, right? So this is what the picture looks like if we draw a system boundary A. If we draw a system boundary B, the only place that we can store energy in the system is actually inside of the mass, right? In the kinetic energy of the mass. So at this point, we'd say the energy of the system is simply the kinetic energy. But there's a flow of energy into and out of the system through this interaction, right? If I actually think about the fact that the mass is connected to the spring, the mass can pour energy into the spring, or vice versa. So then my sort of stock and flow diagram for this would look something like this, right? I can get it, pour energy back into the rest of the universe, or get energy pulled out of the rest of the universe into the mass. Now, clearly, this sort of first framing that I talked about, where you're sort of keeping track of the energy flowing back and forth between different parts of the system, tends to be a little bit more useful because of the fact that you actually can say that the total energy is constant. And that's why when you talk about where your system boundaries are for doing energy conservation, you often are including the interactions inside of those system boundaries.